Okay, ladies and gentlemen, welcome to this episode. We are going to take a look at the Doppler effect for a stationary observer, what it is, how it works, and the equations that are required to actually calculate the changes in frequency and wavelength that are associated with it. So let's get started. Okay, so the Doppler effect is the apparent change in frequency and wavelength of waves due to the motion of two objects, or an object and observer, relative to each other. Okay, so if I have something that is emitting waves, okay, so we'll call this our emitter over here, give it a nice color, a little red emitter, and over here somewhere we have an observer. We'll make our observer a little bit more obvious by making it a little stick person. It appears to have a very red face, which we'd like to probably change. There we go. Okay, so our emitter here is going to send out waves. Okay, and let's imagine that it sends out pulses of waves. Those waves will go in all directions, and will be traveling at a speed of, let's say, v. Okay, so this is imagine you're standing. It could be maybe a little ambulance or something like that. There, this is you standing on the side of the road. If the ambulance is sitting still with its sirens blaring, you get that kind of nee-naw effect going on. All right, the waves are traveling at speed v. The speed of the wave is, let's call it a sound wave, say 330 meters per second. And that is independent of whether the object is moving or not. And that's really, really, really important, that once the wave is created in whatever the medium is, the medium decides what the speed of the wave is. A sound wave in air travels at 330 meters per second. It doesn't matter whether it comes out of a stationary object, an object moving at 100 meters per second, or an object that's even supersonic. Okay, it doesn't matter. As soon as that wave is created and hits the air, it travels at that. I can't stress that enough. When we're talking about waves, they are medium dependent. The motion of this doesn't affect the speed of the wave once it is produced. Okay, so the waves will then travel towards, or we're going to draw them as plane wave fronts just for the sake of it. So if we are stationary, our wave fronts move towards our little observer, and they go bing and bing. All right, this is your knee and your naw as it arrives. Okay, so it goes knee, naw, and then the next one come on after. Now, what we're looking at is, well, what about the situation where the ambulance is traveling towards you? Okay. Now, the interesting thing is here, I can keep this group together and copy it. Okay, so we can compare later on. If we produce these waves, and let's say they have a set time period, because they will do, they're being produced at regular intervals, say they are, I don't know, 0.5 seconds apart. Okay, then the wave here, the very first wave, is produced and travels forward at 330 meters per second. And then the second wave is produced 0.5 seconds later. Now, the issue here is that 0.5 seconds later, the ambulance is no longer here, but has in fact moved some distance forward when it produces its second wave. Okay, so the time between the waves is still 0.5 seconds. Okay, the time between these things is still 0.5 seconds, but they are now closer together. Okay, and when they arrive, therefore, their time of production is 0.5 seconds. When they arrive at the observer, they will appear to be shorter in wavelength and hence higher in frequency. Now, it's important to note that the time now between these two waves is not 0.5 seconds. They were produced 0.5 seconds apart, but because they're both moving at 330 meters per second and their distance between them is now smaller, their actual observed frequency is going to be different. And that's what we're going to try and work out today, because we need to know the relationship between v, the speed of the wave, and the speed of this object. We'll call that v object. And how does that affect what we hear? Because as objects move towards us, the sounds that they emit appear to be higher pitched. And as they move away from us, the sounds that they produce appear to be lower pitched. Okay, this is the classical nee-naw, 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 nee-naw. That's the sound of an ambulance approaching you and then leaving you. Good impression, I know. But in reality, the guy inside the cab, the person who's traveling with the ambulance, hears nee-naw, nee-naw, nee-naw at a completely regular set of intervals. So the observation of this is different. And this is important because we can then use that to work out how fast an object is moving away from us. If we can get this relationship, we can work out how fast it's coming towards us just from the waves that it emits. And then from an astronomy point of view, we can use that to calculate how interstellar objects are moving relative to each other. Are they moving away or are they moving towards each other? Okay, so let's get ourselves set up with a similar diagram to what we had the last time. So we're going to have an object that's doing some emitting. We'll make it a little bit less of an aggressive color, a little green. And then we'll have an object that's doing the observing. I see no reason why we can't have this as a little green alien. Okay, observer. Let's give him an extra arm because he's an alien. Or she, or, non-defined. No reason why it would necessarily have to have a gender-specific object. Anyway, so we're going to start with the concept then that we're going to have an observed wavelength and an actual wavelength. Yep, that makes sense. And the observed wavelength is going to be different from the actual wavelength by this equation. Okay, that the observed wavelength, lambda observed, is equal to the actual wavelength, lambda actual, minus V source t. Now, what the heck is V source t? Well, this is simply a result of distance. Okay, so if this object wasn't moving at all, then the observed wavelength would just be the actual wavelength. Does that seem reasonable? However, what's happening is because this object has, so this would be like lambda natural here. Okay? But this object has created a wave, then moved itself forward some distance. Call that d. And then produced its next wave in such a way that the new lambda is going to equal the old lambda, or the stationary lambda, minus the distance. Yep, because it's now a distance d closer than it probably should have been. And of course, from our speed equals distance over time equation, distance equals speed times time is true. So we're going to replace new lambda because that sounds a little bit non-sciencey. We're going to call it lambda observed. That's what this person's actually going to see. They're going to hear or see, or whatever it happens to be, the new wavelength rather than the actual. So the new wavelength, the observed wavelength, is going to equal the actual wavelength. Take away the distance d. The distance d is going to be what the velocity of this source object is, what our emitter is. So we'll call this our source, multiplied by capital T, the time it was between the waves, the time period of wave production, T. And that's T for the source, as opposed to whatever it observes T to be later on. Is that right? Okay, from here on, it's just maths. We have now, this is what the Doppler effect is. And we can work with that. If we know lambda observed, we know the velocity of the source, and we know the time period between them, we can actually work out what the original wavelength was. But we probably don't know that. So we'll want to put this in terms of other things. Okay, so we can write that as lambda observed equals V wave times T, because V, and we'll just show you why that is V equals F lambda. Agreed? So the velocity of the wave, V wave, is going to equal the frequency of the wave times its actual wavelength, lambda actual. All right. Now we want an expression for frequency probably more than we want an expression for lambda to start with. So we're going to write this then as v wave. Frequency is 1 over the time period. So that's 1 over t times lambda actual. I can actually get it. Close brackets in there. That's better. V wave is 1 over t lambda actual. Now, a little bit of cross multiplying then, multiply both sides by t. That gives me that V wave times t is equal to lambda actual, which is all we've done here. We've replaced lambda actual with V wave t. The speed of the wave times its time period. Okay, are we happy enough with that? Now, since we have v equals f lambda, f equals v over lambda. Okay, so just applying this to this side of the equation, we have that f observed, because remember we're trying to replace lambdas here with frequencies, that the observed frequency is going to be the speed of the wave divided by the observed wavelength. Okay, it's not the observed speed because remember the speed of the wave is always just the speed of the wave. That sound wave travels at 330 meters per second, that's that. Light wave travels at 3 by 10 to the 8 meters per second, that's that, regardless of whether you're moving or not. Okay, that allows us to replace lambda observed, okay, because we can cross multiply here to give us lambda observed equals v wave, okay, and that gives us this equation. All right, that may take a little bit of maneuvering, but we can do this, okay, because all we do is take our expression here that says lambda observed equals v wave over v source, and we replace lambda observed here. Okay, see what I've done? I've taken lambda observed and simply replaced it with v wave t minus v source t. Okay? Hope you're following this. Yeah. At this point, if you're not following, put a note in the comments below and say lost you there. But wind back a bit, and we'll be all right. All right. So we've got a common factor of t here on the bottom line. So we can take out a common factor of 1 over t. I'm going to try and neaten this up a little bit, make it look a little bit nicer. So that will give me f observed stays the same as it is equals v wave stays where it is. V wave in the bottom stays where it is, V source stays where it is. I've just brought out these two t's here. So I've brought out this t and this t, and because they're in the bottom line, they come out as 1 over t. Okay, and that gives me that equation. Alrighty, moving on then, we want to change that because 1 over t is f, isn't it? Okay, so that's good news. So we can go that we can replace 1 over t with f wave, okay, because t is the time for the actual wave. So 1 over t is not f observed, it's the actual frequency of the actual wave. So actual wave frequency is multiplied by the speed of the wave over the difference between the speed of the wave and the speed of the source is equal to f observed. And we could stop here. And we will stop here because this is fine. This is disgusting looking, so we're going to make this look a little bit nicer. Okay, instead of f observed, we're going to change that to f, and then we're going to put a little dash up high called a prime. We're going to call that f prime. Okay, f wave, we don't need the subscript wave, we just need f. Anytime we use f or v, we're talking about the original wave produced. The same goes for v wave, we just replace it with v, replace that with v, and then v source, we're just going to shorten that now to v subscript s. And what that'll do is it gives us a new equation, okay, where we've replaced f observed with f prime, f wave with f, v wave with v, v wave with v, and vs with vs. We can further simplify that to v over v is 1 minus v over vs and separate this fraction out. Either of these is completely acceptable though and looks quite pretty. What's the purpose of this? Well, if we happen to know what the speed of the wave should have been and what its frequency is, and then what we observed, we should be able to work out the speed of the source. And that's something that can be done when you're looking at spectroscopy lines. That if you have, say, the line spectra for a particular gas that you happen to know, and then you observe it from a distant object, and you find that the frequencies are in different places. But the pattern is the same, so you can find a nice average value. You can find your observed frequency, which is what you see here. So observed. So that's going to be f prime. You've got your actual frequency, f, so we're doing quite well. We know the speed of light in a vacuum, so we've got the speed of light in there. So job's good. We would be able to find the speed the source object was moving at. And that allows us to calculate the speed at which objects in space are either moving away or moving towards us. Okay? Now, that's nice, but we want to further this because maybe we don't have the frequency, maybe we want to rearrange this for lambda. Okay, so we want a frequency set of equations, which is these. Note these, you will need them. You will need them, but we want to make ones for lambda. Okay, so let's take these with us and take a nice new page. Okay, now for lambda, it would have to be true. In fact, it is true from our previous work that lambda observed is going to equal v over f observed. Notice that it still remains as v because the speed is constant for everything. We now have f observed. We have both of these equations that we want to use. So I'm just going to replace f observed with this on the bottom line. Okay, and instead of lambda observed, we're of course going to call that lambda dash from the word go to save us writing the word observed all the time, which is just annoying. Okay, so that gives us that lambda dash, lambda observed that is equal to v, which stayed in the top line and nothing happened to it, upon this. Just highlight that so we can see it. This is just this on the bottom line. Okay, so we've just replaced f observed here with our actual function for f observed. And that's lambda dash. You can walk away from that, but we don't want that. We certainly don't want an f here because then we have lambda observed in terms of frequency original. We want lambda observed in terms of lambda original. That would make a much better situation for us. Okay, so we're going to use the fact that f equals v over lambda, okay, from just the regular wave equation, and we're just going to replace f. So we're going to replace f with v over lambda. Everything else has stayed the same. Okay, now that has the beautiful effect of cancelling top bottom. So I can divide top and bottom now by v. See that? I can divide the top and bottom of that equation, and the rest of this game is now going to be making this look like something that we would want to use. Okay, so if I get that, then my v here becomes a 1, my v on the top line becomes a 1, and I now have this situation. Now, I don't particularly like having a 1 over lambda situation going on here, so I'm going to multiply the top of this equation by lambda, and of course, because I've multiplied the top of the equation by lambda, I must multiply the bottom of the equation by lambda. The result of that will give me, it'll put a lambda there to give me lambda over lambda, which will destroy that that fraction, which is what we're after. And that will give me a slightly different equation, which is this. Okay, notice that we now don't have this term at all, but this term on the top, this 1, has now become a lambda. Now I'm in business because I've got lambda observed in terms of lambda original. I've got it also in terms of the speed of the wave and the speed of the source, the speed of the emitter. I could stop here. This is fine. This is absolutely fine. We could just go tick, job's good. But we've got a fraction on our bottom line of a fraction, and that just doesn't sit right with me. We don't like that at all. So we're going to go a few steps further to make this a little bit prettier. So we're going to multiply the top line by Vs, and we're going to multiply the bottom line by Vs. Okay, because that's our problem, our little Vs in the bottom line. We want rid of that. So we're going to multiply top and bottom by Vs. And when I do that, I'm going to get something that looks far worse, but trust me, in the long run is going to be much better for us. Okay, we get lambda Vs upon Vs and all that. Multiply into my bracket and have an act of faith that this is going somewhere. And we get this, that lambda dash is equal to lambda Vs over Vs upon Vs, V over Vs. There's a lot of Vs's there. But we can now start cancelling those Vs's. And specifically, it's these two that I want to cancel. And I want to cancel them so much that I'm going to put them in a completely different color so that they stand out. It's this and this that I want to cancel. Okay? Because what that does is it eliminates my fraction on the bottom line, which is what this whole game was about in the first place. Now what I want to do is I want to rewrite that, and I get this. Okay, I've got lambda Vs over Vs minus V. Okay, we're so nearly there now with this. We're going to take lambda outside the bracket there so that all of our stuff to do with speed is in a single term. And I've got this. That lambda upon Vs over Vs minus V. Okay, which is the speed of my emitter over the change in speed compared to the actual moving object. That seems like a weird equation to have, but then once I do Vs over Vs is 1, I end up with this, my final expression. That lambda observed is equal to lambda original upon 1 minus Vs over V. Okay, which sort of makes sense because it's the observed wavelength is the regular wavelength multiplied by some percentage less that, due to the fact that the object is missing or the object is moving towards you. Now, if the object was moving away from us, this whole reasoning is exactly the same, except this becomes a plus. Because the wavelength will appear longer. And up here, this becomes a plus. Is that all right? Okay, so this is how to calculate the frequency and the wavelength of a Doppler shift for an object that's moving towards a stationary or away from a stationary observer. For a little bit of fun, you could start from first principles, this idea here, and what if the observer was also moving? Okay, the hint here is, how would you be able to tell the difference between that and if this was moving towards you with a speed v and this was moving with a speed v towards it, how would that be different from a source moving at 2v? I'll leave that one with you. You can have a little bit of fun. For now though, remember that f observed is equal to f original multiplied by this, and that lambda observed is equal to lambda actual multiplied by this. Okay, it's been an absolute pleasure to see you again. Please like and subscribe, and don't forget that physics rocks. It's true.